Okay, I think we can get started. Welcome everybody. Thanks for coming. Today we have Moisès Coll Macià giving a talk on different generation intervals among non-African human populations. Moisès is a PhD student at the Bioinformatics Research Centre at Aarhus University. He's advised by Mikkel Heide Schierup. He's worked on different projects related to Neanderthal admixture, selective sweeps, and sex chromosome evolution. And he's visiting my group for a few months here in Copenhagen, virtually. We're very excited for the talk. So the talk will be recorded, and I think we'll upload it in Glow Institute YouTube channel afterwards. But yeah, Moisés, take it away.
Yeah. Thank you, Fernando, for your introduction. And good morning, everyone. So as Fernando said, I'm a PhD student with Mikkel Heide at Aarhus University. And during my PhD, I've been involved in different projects, but one of the most interesting projects I feel I've been working on is this one that I'm going to present you today, that we entitled as different generation intervals among non-African human populations during the last 40,000 years of evolution. And we see this signal from two independent sources of our genome, one being the recombination clock and the other one, the mutation clock. Let's see. Okay. So we started this project because some time ago, Laurits Koh, a former postdoc in my group, he developed this two-state hidden Markov model that would try to classify a human genome into two different categories, either archaic or non-archaic. The way this model was doing that, so let's say we have this demographic model where we have humans. Here we have the Neanderthals integrating into non-Africans after the out of Africa, and then this African population. So this model works in a way that here what we have represented is an example of a genome coming from a non-African individual. And then from here, what we see is in little circles represented some SNPs. So we would remove, first of all variation that is shared with an African, with the African outgroup. And then, as you can see, as shaded SNPs, then all this variation would be removed, and we would make a clear distinction between two different ancestry backgrounds. So the one that is the human one, it would be less dense in SNPs, so as represented here in white. And the one that is coming from the Neanderthal lineage, since it had more time to accumulate all this variation, would be more dense in SNPs. So then this two-state hidden Markov model will classify the genome divided in windows into Neanderthal windows or archaic windows and non-archaic windows. So it's also important to notice that here we don't use at any step any Neanderthal reference genome or archaic reference genome. So our model is not going to be biased towards one of the reference Neanderthal genomes. So we ran this model in the Simon Genome Diversity Project, and we check. So what you are seeing here is the individuals that we check the archaic fragments for. And what you observe here is so they are colored by the mean archaic fragment length. And this was quite striking because, as you can see, populations that are on the West, they seem to have shorter fragments than populations that are in the East. And then we started thinking, what could cause this pattern? So one of the things that we started thinking about was that, as we know for other studies different from ours, is that the archaic fragment length is informative of the number of generations that pass since the admixture event. So if we imagine that we can sample haplotypes backwards in time, then at the time of admixture, at this point, we would potentially sample a whole Neanderthal haplotype, and then in each generation, this haplotype would be broken down into smaller pieces by recombination. So the number of generations is proportional to the fragment length of these Neanderthal fragments. So we thought that maybe there was a difference in the speed of recombination to explain this pattern that we were observing. And this is the hypothesis that we proposed. So it might happen that, so assuming that there was a single pulse of Neanderthals into the common ancestor of the two populations, here represented as POP1 and POP2, then the fact that they had difference in the fragment length, in their genomes of Neanderthal fragment length, is indicative of that they had difference in the number of generations since this admixture event. Then once we observed this pattern, we wanted to see if this was consistent for different filters, if it was and if it was robust. So the first filter the first test that we checked was that instead of using the mean, that can be sensitive to outliers. So saying that East Asians, if they had for some reason much longer fragments, or like a few much longer fragments, then the mean would be kind of biased. So we used the median instead of the mean. And we observed that even using the median that is much more robust than those outliers, we still see the same pattern. Then we used only archaic fragments that we comparing to the three archaic genomes, reference genomes, were much closely related to the Bindia. So we compared to the Bindia genome, to the Altai Neanderthal genome, and also to the Denisova. And we checked only for the Bindia-like Neanderthal fragments. And we observed that this pattern still holds. So meaning that if we disregard other possible events, for instance, we know that in East Asia, they have an extra component from a Denisova that in Europe is not as present. So by checking these only Bindia-like fragments, we discard this extra admixture that they had from Denisovans. And we still see this pattern of difference in mean fragment length. And then our model outputs mean posterior probability. So in a way, it gives us a sense of confidence in for each fragment. And then by using only fragments that had a posterior probability higher than 90%, so in a way saying high confident fragments, we still see the pattern. So in a way, we are quite sure that there's high differences in mean archaic fragment length in Eurasia. So then what we did was to divide these different individuals in the 5 main regions. So the 5 main regions are West Eurasia, South Asia, America, Central Asia, Siberia, and East Asia. And then we checked for this archaic fragment length, we checked 3 statistics. The first one, as we saw, is the mean archaic fragment length for each individual. And then we have the number of archaic fragments and the archaic sequence. So basically getting all the fragments, summing the length of those, and then that would give us the total archaic sequence per individual. And what we can observe is that these distributions are quite different for all these 3 statistics. And if we look at the most extreme distributions, we see that West Eurasians and East Asians have a difference on the mean archaic fragment length of about 12%. And for the archaic sequence, this difference is around 32%, which is quite striking. And we wanted to check if, because so at this point, we thought that maybe there was some other explanations to explain these differences that we observe in this slide. And one of them could be, for instance, if East Asians had a private Neanderthal admixture or archaic admixture that would give them more archaic sequence, as we can see here, and also because this second admixture would have happened much more recently, those fragments would be much longer, and then we could also explain this pattern here. So what we did was, instead of comparing in an individual level, what we did was to compare in a population level. So the way to do that was for each population, here in blue is West Eurasians and in green is East Asians, was to take all the individuals in that population and join all the fragments that overlap. that would give us this joint set of fragments, and then we computed the amount of archaic sequence for each population. And we can see already that this is not that different. So when we compare West Eurasians with East Asians, there's a difference of 5% in this population level difference. Sorry. That is contrasting quite some with what we observed before, of this 32% difference in the individual level. And then what we did was to divide these joint sequences into shared and private sequences. So by basically comparing the joint set of fragments of the two populations, then we divide subsequences of those into shared if they were overlapping, or private if they were not overlapping with another sequence in the other population. And these are represented here. So the shared sequences for each population are in this more colorful color in each bar, and the private are these parts on top. So this is telling us that most of it for each population is shared in the two populations, and there's no a great excess of private sequences in East Asia. So at this point, we thought that by doing this population level comparison, it's quite unlikely that there was a big private event into East Asians, because then we would expect a much higher level of private sequences in that population, instead of seeing what we observe here. But then we wondered why we saw this difference in the population level analysis and the individual level analysis, this 32% against this 5% difference in these two populations. And then what we did was to check the frequency of the fragments. The way to do that, so if we take, for instance, East Asians here, we divided the genome into 1 kb windows, and then we check for each window how many individuals had an archaic fragment. So we can see here, for instance, in this window, there's only one individual that has an archaic sequence. So the frequency for this window would be 1. And then this one, we see 3 individuals having an archaic sequence. And that would draw what looks like a side frequency spectrum, but for fragments, so a fragment frequency spectrum. And this is drawn in this figure that you see here in the right-hand side. So what we observed, the means of these two distributions are shown in these more plain lines. What we see is that East Asians are more shifted towards higher frequencies than West Eurasians that shifted towards lower frequencies. So what we can explain, so we explain this difference in the population level analysis compared to the individual level analysis by this difference in frequency. And this is consistent with an hypothesis, well, the dilution hypothesis that is, it was hypothesized by Joseph in 2016. So in this scenario, what we would have is, after the out of Africa, there would be a split between this basal Eurasian population and then the rest of non-African individuals. And then in this common ancestor of West Eurasians and East Asians, we would have an admixture of Neanderthals. And then after the split, we would have a subsequent admixture from the basal Eurasian population that doesn't have this Neanderthal component into West Eurasians, diluting the Neanderthal component that was in that population already. So looking at the fragments, what this dilution would cause is the following. So for each individual, we would have less Neanderthal, as we observe here. So, and however, if we look at the population level, we see that they have similar Neanderthal content when we compare the two populations. But for each individual or in the population level, we would see a decrease in frequency. And this is actually what we observe in our results. But this dilution hypothesis would not, or we wouldn't expect that there was a big shift on the fragment length that we observed at the beginning. And what we did to compare in this more population level comparison that we were doing before, so what we did was to compare overlapping fragments among populations. So if we take one individual from West Eurasia and we compare to the joint fragments of the other population, then we would divide them into shared and private. And then if we compute the mean archaic fragment length of these shared fragments, this is what we observe in this image here, in this plot, where we see still this 12% difference of the mean archaic fragment length. So even though we focus on fragments that overlap, so they are more likely to come from the same event, we still see these great differences in the mean archaic fragment length. So we were able to explain why there's great differences in the amount of Neanderthal in these populations, but we still, so what we thought is that these demographic events doesn't explain this mean archaic fragment length, but instead is the first hypothesis of the mean generation time being different among these populations. And to test for that, what we did was to analyze some ancient humans. In this case, we have Ustishin, Lochburg, and Stuttgart. In this left panel, archaic fragment length that we find in Ustishin. First of all, this individual is a 45,000-year-old individual, and of course, since this individual died a few thousand years after the admixture, as we expect, this individual should have long fragments compared to people living today, and this is what we see here. But then when we compare the Lochburg, that is a hunter-gatherer, European hunter-gatherer, and Stuttgart, that is a farmer, also European. So these two individuals are much more related to this West Eurasian population. Then what we see is that, of course, compared to this distribution, this population have a much, or they have longer fragments in comparison, because since Lochburg is a 8,000-year-old sample and Stuttgart is a 7,000-year-old old sample, then of course they should have longer fragments compared to their relatives. But when we compare to other populations, in this case with East Asians, we see that Lochburg has a similar level of mean archaic fragment length compared to East Asians. So this is telling us that roughly the difference between this mean in this distribution and this mean in this distribution, so the difference in the mean archaic fragment length between East Asians and West Eurasians, if caused by differences in generation time, would be about 8,000 years of recombination. So this 8,000 years of recombination means that since admixture, West Eurasians would have had 275 generations more, and meaning that their generation times would be around 20% different between these two populations. At this point, we were quite happy with our results. We were quite convinced, but we still wanted to see if we could dig up some more information from those genomes that were independent from this fragment length or the recombination clock. And we found the option to do that with the mutation rate and spectrum. And this is because from the trio studies, in this case, I'm citing Johnson et al. 2017, is a trio study basically that they show that there's a linear relationship between the parental age and the number of de novo mutations that are transmitted in a single generation. And this would translate to basically, with an increasing parental age at conception, there would be a decreasing mutation rate per year. So if our previous hypothesis was true, then populations that are predicted to have shorter generation times would have a higher mutation rate per year, and therefore more accumulation of derived alleles. And then we also know that from the same publication, we learn that there's a change in the mutation spectrum. So this is basically that depending on the parental age, for instance, if we take the T to C mutation, the T to C transition, we would have that for a certain parental age, let's say a younger parental age, we would have a certain fraction of the novo mutations being of these T to C mutations. But then if this parental age increases, then we would also increase the fraction of T to C mutations. So we should be able to see some signal in the mutation spectrum related to these expectations of changes in generation time. So the way to do that, the way to inspect for that, was to get all the derived alleles that we find in the individuals that we check in the Simon Genome Diversity Project, and then we polarized all these polymorphisms comparing to chimp, considering chimp being the ancestral allele. Then we discarded all alleles segregating in Africa. So if an African had one of these polymorphisms, we would remove that from our dataset because we believe that this change in generation time would have happened after the out of Africa, and therefore that would give us much more resolution on what happened to these derived alleles after this out of Africa, and therefore those alleles being influenced more by the change in generation time. And then we also masked regions of repetitive nature, and also regions that there was some evidence of Neanderthal or archaic introgression into one of the or any of the individuals that we analyzed. So for instance, here we have this region being of Neanderthal origin, and therefore this would be masked in all individuals in our dataset. This last step, this Neanderthal masking, what ensures is that this part of the analysis, so this mutation study, is independent from the previous one, from the fragment length distribution. So then we checked the accumulation of derived alleles, and we see that there's a different distribution depending on which region the individuals are from. So if we still compare, as we were doing before, West Eurasians and East Asians, we see that East Asians have a lower accumulation of derived alleles, and that would correspond to those individuals having a smaller mutation rate compared to West Eurasians. And that is actually the expectation that we had from the de novo mutation studies, from the trio studies. But then to get a more quantitative sense, what we did was actually from the linear relationships that they derived in this paper, we got this formula that basically tell us the expected generation time, the expected mean generation time for the population, depending on the other population generation time, and the difference in the derived allele accumulation. And also we had to assume some split dates for this to account for these differences in derived allele accumulation. And then by plugging in these numbers into this equation, basically what we did was we assume some reasonable generation time for East Asians, and that would give us a difference of 3 years of generation time for West Eurasians. So when, for instance, East Asians were, so when we assume, for instance, that East Asians are have a 28 generation time or generation interval, then we would get back from this equation 25 years of generation interval in West Eurasians. So this is telling us, as we were seeing before in the fragment length distribution part of the analysis, that West Eurasians seem to have a much shorter generation time than East Asians. And then turning our attention to the mutation spectrum, as I said before, keep in mind that individuals, or when mothers and fathers are much younger, they tend to transmit different proportions of each mutation type. So for instance, if we take as an example the T2C mutation, then when the parental age is of younger ages, they transmit less T2C mutations than when we get other parental, like older parental ages, that they tend to transmit more, proportionally more T2C mutations. Because this plot that I'm going to present here is a bit composite, I'm going to go step by step. So first of all, what we did from all the derived alleles that we obtained from all the filtering processes that I was explaining you before, we classified them into these 6 mutation categories. Then these C2T mutations, we divided into 3 categories. The first one being CPGs to TPGs. And we use this independent category because we know that these mutation types seem to be evolving under different mutational processes. And then we also classify these C2T mutations into these TCC to TTC mutations, because we know that this mutation type is, or mutation signature is enriched, is highly enriched in Eurasians, or in Europeans. So Europeans tend to have an enrichment of this mutation type compared to other populations in the world. And we wanted to know if, or what was going on with this mutation, and if we were able to explain partially this enrichment in this population. And finally, this third category would be the rest of C2T mutations. Then for each panel, what you will have is two plots. This one here, the decode plot, so the sub panel, that would be basically this panel, as you see here. So what we did was to take the decode dataset, but instead of plotting the so a linear relationship for each parent, what we did is to get the mean of this of the parental age, and that would give us this linear relationship here. And then for the Simon Genome Diversity Project, the dataset that we are processing, so what we show here is the correlation between the mean archaic fragment length and the derived allele fraction. And we used mean archaic fragment length as a proxy for the mean parental age. So in a way, if what we try to do here is to see if we have similar patterns from the decode dataset in a single generation compared to the Simon Genome Diversity Project dataset that is recording for multiple generations, but we would still expect to capture this difference in generation time. Then if the Simon Genome Diversity Project dataset correlation is significantly different than 0, then you would have an asterisk here. If the decode is also significant, you would have an asterisk here. In this case, since it's not, you don't have it. So let's see what happens when we show all the panels. So what we see is that most of the mutation types seem to correlate or have similar patterns of variation. So in the 2 data sets. So you can see that when the 2 correlations are significant, here for instance, then the 2 correlations seem to have a similar effect. So either positive or negative correlations between the 2 data sets. This is telling us that the variation in the mutation spectrum, if we assume that this is a good measure of generation time, then is telling us that the variation of the mutation spectrum seems to be affected by these differences in generation time in these populations. So West Eurasians seem to have a mutation profile similar to young parents have in a single generation, and East Asians seem to have a similar process compared to older parents. So this again seems to point towards a differences in generation time among all these populations, and the fact that there's a perturbation of these two variables, the derived allele fraction and the mean archaic fragment length, and that seems to be quite similar to the data from a single generation, so from the DIGO dataset, seems to be confirming that there's a difference in generation time among these populations. So a summary of our study is that we used, first of all, Neanderthal fragment lengths to show that there's a mean generation time differences across Eurasia. And we also used, as I showed you, different ancient individuals to show how these fragments were evolving in the West Eurasian population, and we saw that this was compatible with a difference in generation time. Then we also used the mutation rate and spectrum independently from the Neanderthal fragment length or the recombination clock part of the study, and it seems to also follow the expected patterns of change in generation time. And for this study, we used the Simon Genome Diversity Project, and we grouped them into these 5 main regions. We think this might be a limitation of our study, because we know that all the populations that are inside these regions or that are grouped in these regions might be quite heterogeneous. So probably that would decrease the resolution that we have in this study to give more quantitative results. And therefore, in future studies, we want to analyze other datasets, for instance, the HGDP dataset or the 1000 Genome projects together, and see if we can get much more signal out of it. And then also for the future, we would like to see if we can correlate all this variation with different cultural changes, differences in climate, or the demography, that they are quite described for different populations. And with that being said, I would like to thank all the people involved in this study. And I would be happy to get any question.
Thanks, Moi. That was a great talk. Thank you so much. Do we have any questions?
I have a question.
Sham?
It was an excellent talk, really interesting stuff. And I would love to chat with you later on at some point.
Sure.
But I have a quick question about another way we can look to see if the differences in generation time is having an effect as well. Instead of looking at the archaic fragments that you saw across Eurasians and East Asians, West Eurasians and East Asians, another way would be to mask out the Neanderthal fragments and look at the recombination landscape across the non-archaic fragments in all of these populations. Because if you'd expect generation time to be shorter in West Eurasians, you would also expect much higher recombination rate across the genome, right? Obviously accounting for hotspots and stuff like that. And we know already that Africans and Eurasians have different recombination maps, so they don't look very similar. So I was wondering if a fine scale look at recombination maps across East Asians and West Eurasians would confirm this hypothesis, because I think it's a hypothesis that challenges a lot of the assumptions we make across all of our different studies. So I think it would be really nice to look at a few more ways of confirming that what we are looking at is correct.
Yeah, totally. I agree. But I think it's not as easy, I would say, to compare the different recombination rates and maps. So I think that would be a whole project in itself. But it's true that
I would agree.
Yeah, but I would also expect what you said, that we should see all these differences in recombination rate and maps. Totally.
I think we have a question from Fatima.
Hi,
Hi.
Thanks, Moisés. That was such a nice talk. It's a super interesting project. I have two sort of silly or simple questions. One of them is, do you think that this was some sort of a phenomenon that happened as a pulse? Like there was a specific period of time where the generation time in West Eurasians was lower than in East Eurasians, or whether it was something that actually has been happening for the last millennia in these populations, and that it might actually apply to very recent times. That's one of the questions. And another question is, I know you say that you still have to correlate this phenomena with cultural factors, climate, demography, etc. But if you had to guess, I'm just so curious. I would just like to know on the spot, why is it that generation time is lower or has been lower in West Eurasia? So if you had to make a guess, what would you say?
So yeah, this is actually is something that we trying to say more about in this project, but right now we are not able to say anything because that would be, so anything that we say would be speculations, of course. But we think that during the last 14,000, and maybe you might know, people attending today might know more, but I think one of the biggest changes that we had in human history has been farming. So what we would like to see if farming was causing all these changes, because we would expect that if you have more resources, so you have more access to food, then maybe you were able to have children much earlier, and therefore you would decrease the mean generation time. But we still have no exact idea on why there were these changes. Also, there's people that say that these cultural changes shouldn't affect that much what we observe. But in my case, I disagree. But I still think that what we can say right now are all speculations.
Can I ask one question, then
Yes.
I'll pass it on to Sham? Could you look at ancient East Asian genomes, so at least like bound this process to see, like, ancient genomes from like 3, 4, 5,000 years ago have the archaic length that would be consistent with this happening for a long time?
Yes, so this is something that we tried because so Ben has this frog program. So we played a little bit with ancient genomes from all around the world, but the estimates that we have from this method, they are not as, how do you say? The confidence intervals for each individual are kind of variable. So we were not able to get more information out of it. So that's why we limit our studies with these 3 ancient individuals, because since they are high coverage, we were able to run Lauritz method into these 3 individuals. But yeah, like including much more ancient genomes, I think it's going to be really valuable to see how these fragments look like in the past, especially in East Asia, that we don't have in this project information right now.
Sham?
Yeah, I have a few questions, and if I'm hogging up the questioning time, let me know, Fernando, and I'll shut up and talk to him later. So my first question was about about the different mutation classes that you were looking at to compare whether the parental age correlated well with the archaic fragment lengths. I know from the decode paper that there are a few mutation classes there which differ quite a bit between the maternal and paternal side. So you don't tend to transmit as much of the C to T and as much of the T to C. They're very different whether you're an older father or older mother.
Mm-hmm.
And I was wondering whether you could leverage some of this to see if the differences, if there was any sex bias in the age of what the parent was, and if you also looked at sex chromosomes, because sometimes this thing will get washed out because we're going to transmit.
That's actually, so yeah. I didn't want it to include this in this talk, but okay. That's actually something that we also looked a little bit.
It seems to be X seems to be different.
Yeah, so we check different sex-specific mutation types. For instance, the X to A ratio, because we know that, so there's 3 X chromosomes for every 4 autosomes. And then because of the pattern of inheritance of these X chromosomes, we would see that the maternal has more to say on how this chromosome mutates, right? So then comparing X to A ratio, then we see differences on the importance of the age of the maternal age and the paternal age.
Yep.
So we try to investigate for these kind of mutations. Also, there's this C2G mutation that is, so it increases a lot with maternal age. Even there's a paper that says that it's probably, this increase is not linear, it's actually quadratic. So maybe it could be that, so something that we try to find is if there's an enrichment of this type of mutation that would be indicative of much older maternal ages than other populations.
Yeah. And the other question I had was related to what Fatima brought up and what you were discussing about whether this was a pulse or it was what kind of timing events can we say about when these generation times were different. So going back to the early pictures that you were showing, where you were showing the amount of shared archaic fragment lengths and the private archaic fragment lengths between East Asia and West Eurasia, I don't think you need to go back to that. I kind of, actually, maybe it's not a bad idea to look at it. I was wondering, given that the shared content seems to be about the same and the private thing seems to be quite different, it also tells us something about when this would have happened. It can't be very old, because then you would imagine that the amount of shared is far lower, because you would start breaking down in the West Eurasians, the fragments that are being shared across the different individuals. So it can kind of, maybe through simulations or some other similar tool, because I can't think of an easy analytical way to think about how to quantify this. We could maybe quantify at what time the generational differences start.
Mm-hmm.
So that could be, that might answer the question of whether it's related to any kind of cultural transitions, including the Neolithic transition.
Yeah, so at the beginning of the project, we tried to use simulations to try to fit different models. But the thing is that with simulations, you can fit any demographic model that you want. And then it's a bit kind of fishing out the hypothesis that you prefer. So we decided to be a bit agnostic of any simulation part of the study and be more about what the data is telling us directly. But it's true that there's potential for simulations to show for these different demographic scenarios and stuff to see if we can fit the data and so on. I think that would also be a really cool part of the study.
I'm just curious about the differences in the private versus the shared amount that you see, right? That must say something about the timing or about the number of offspring.
Yeah.
Or some structure.
Mm-hmm. Yeah, I agree. But so we started doing loads and loads and loads of simulations. There were a bunch of models that would fit, but we weren't convinced that that was giving us really insightful information at that point. But I think that should be tested again. So we should do something about these simulations. I totally agree.
Can I ask, you don't mention Oceanian populations at all? And I'm guessing that's because you were worried about confounding with Denisovan mixture, but like, can you say anything about whether you think this is a signal that is shared with them?
Yes, that's actually, so we tried to include at the beginning also of this project, the Oceanians, but it made everything more difficult because we know that the component that they have is, sorry, it majoritarily comes from this Denisova admixture. So that was making things much more difficult because then, of course, the poles from the Denisova would be matched recently, and therefore you would expect longer fragments, but you would not be able to say if they were much longer just because of generation time differences or other differences.
If I could add to that, but you can predict from your East Asian data or close related populations what that should look like. So that might give you confirmation.
Yes, totally. Yes. And that's something that we want to do. So this project doesn't stop here. So we are trying to publish this study right now. But we want to extend, of course, this project into more data. And of course, we wanted to include this Denisova component in Oceanians.
Do we have any more questions? Okay, then I think let's thank Moi once again for an excellent talk. It was super insightful. It was yeah, great to see what you've been doing so far. And thanks for everyone for coming.
Yeah, thank you.